In section 1.3, we're going to study the concept of division by zero. So basically, at the end of this lesson, we're going to understand if an x value makes a rational function be 0 over some number, or if an x value makes my rational function be some number over 0, or if an x value makes my rational function end up being 0 over 0, there's going to be different implications for each of these. So we are going to look at each of these different implications. Okay, for meaningful division, when you were taught division back in elementary school, for division to have meaning, there was one result that checked if you divided two numbers together. So for example, 100 divided by 4 equals 25 has meaning because 25 times 4 is equal to 100. Let's take a look at the following function. This is the rational function that's been factored, and we simplified these in pre-calc 20. Now in pre-calc 20, before you could simplify, you had to list non-permissible values. So non-permissible values are anything or any value that makes the bottom equal to 0. So for x plus 3, we could not have negative 3 because that makes my denominator 0, and so too does negative 4. Now, if you notice, the factor x plus 3 cancels out, so we would be left with the rational function x minus 2 over x plus 4. So, because the factor x plus 4 still remains in the denominator, the value x equals negative 4 is going to show up on my graph as a vertical asymptote. The value negative 3, because it's no longer in the denominator and it completely cancels out, it's going to be known as a point of discontinuity or a hole in the graph. And to figure out the y-coordinate of the hole in the graph, we just plug negative 3 into whatever is left in my equation here. And if I work that out, I get negative 5 over 1, which is going to be negative 5. So therefore, the hole in the graph is at negative 3 and 5, and I have a vertical asymptote at negative 4. So if we take a look at our graph, this is what it's going to look like. I created this graph on Desmos. The only thing is it does not show the hole in the graph, so there should technically be a hole in the graph right there at negative 3 and negative 5. Okay, if a value of x makes the numerator of a rational function 0, but does not make the denominator of the function 0, that value of x will be represented as an x-intercept on the graph of a function. And if we look back at this previous example, the value 2 makes the top or numerator of this function 0, but not the bottom. And notice that 2 is an x-intercept on my rational function. So basically, if we get a value of x that makes 0 in the top and not 0 in the bottom, this is going to be an x-intercept. So say we're asked to find the x-intercepts of this graph, okay? And again, in Math 10, we found x-intercepts of linear functions. I believe in Math 20 or in Pre-Calc 20, you found x-intercepts of quadratic functions. So to find the x-intercepts, we have to let y equal 0. So I substitute 0 in for y. I have x squared minus 4 divided by x squared plus 1. So mathematically, I would multiply both sides by x squared plus 1. And on the right-hand side, the x squared plus 1's canceled. The left-hand side, 0 times anything is going to still be 0. So I'm left with 0 is equal to x squared minus 4. Taking it up here, I can factor to get x minus 2 and x plus 2. So therefore, I have two things multiplied equaling 0. So either x minus 2 equals 0 or x plus 2 equals 0. So my two solutions are either x is 2 or x is negative 2. And those are going to be my two x-intercepts for this particular function. So values that make the top of my rational function 0 but not the bottom are, again, shown here to be x-intercepts. If a value of x makes the denominator of a rational function 0 but does not make the numerator of the function 0, then that value of x will be represented as a vertical asymptote. And again, if we look back at our original example here, x plus 4 is my factor. The value negative 4 makes the bottom 0 but not the top, and it showed up as a vertical asymptote. As you can see, there was a vertical asymptote at x equals -4. So if we get a value of x that makes the bottom 0 but not the top, we call that value of x makes our function undefined. So say we wanted to graph this equation. Again, this is a simple rational function. Okay, again, quickly sketching this, the value that makes the bottom 0 is going to be 3. So that's going to be my vertical asymptote. And if you recall from pre-calc 30, this graph is of the form a over x minus h plus k. And since k isn't there, that means I have a horizontal asymptote of 0, as k was my horizontal asymptote. If I sketch this in, I'd get one graph going here. I would get a y-intercept of -2/3, and my second part of my graph would come down something like this. So this would be a quick sketch of this function. And again, the value that makes the bottom 0 but not the top is going to be a vertical asymptote. Finally, if a value of x makes the numerator of a rational function 0 and the denominator of a rational function 0, that value of x will be represented by either a hole in the graph, which is called the point of discontinuity, or as a vertical asymptote. So if a value of x makes both the numerator 0 and the denominator 0, we call that indeterminate. Okay, let's say we're asked to graph the following. Now this should be part of a review from pre-calc 30. So first of all, to graph this, we are going to list we're going to factor, the top. And the top of this rational function factors into x minus 2, x plus 1. Now I'm going to list a non-permissible value. So my non-permissible value is x cannot equal 2. So now we have to figure out, what is x equal to going to be? Is it going to be a POD, or is it going to be a vertical asymptote? Because if I plug 2 into the original equation, notice that'll make that part 0, it'll make that part 0. 2 makes this function indeterminate. Well, if you notice, the x minus 2's cancel, so we are left with a simple function of y equals x plus 1, which is a linear function. So therefore, because the factor x minus 2 completely cancels out, 2 is going to be a point of discontinuity, or a hole in the graph. Figure out the coordinate of the hole, I plug it into the function that's left. So I'm going to end up with 2 plus 1. So therefore, f of 2 is going to be 3. So if I was to sketch this picture at 2 and at 3, I would have a hole in the graph. And my y-intercept for this graph is 1. I get an x-intercept of -1. And if you were to sketch it, it would look something like that. So there would be the graph or sketch of your function. So even though the graph looks like a rational function to begin with, and it is, but because the factor cancels out, it turns into a linear function with a point of discontinuity. Okay, let's take a look at this next example. So in this next example, again, I'm going to factor an x out of the top. So that's going to be an x minus 2. And if I factor the bottom, it actually works out to x minus 2 times x minus 2, which is x minus 2 squared. So now my non-permissible value is going to be x cannot equal 2. Now if I simplify, this factor is going to cancel out one of those, and I'm still going to be left with a rational function x over x minus 2. And because 2 makes the bottom 0 and not the top, and what's left right here, I have a vertical asymptote at x equals 2. So because the factor x minus 2 from the original question didn't completely cancel out of the denominator, the value x equals 2 is going to be a vertical asymptote. So to draw this sketch quickly, at +2, I'm going to get a vertical asymptote. Okay, we also know that I have a horizontal asymptote at y equals 1, and there's a couple ways I can tell, but the easiest way, looking at the original question, because my degrees are the same, I take the ratio of the coefficients in front, and that gives me my vertical asymptote. Okay, and finally, if I want to find my x-intercept, well, my x-intercept is going to be whatever makes the numerator 0, which is going to be 0. So my graph is going to look something like this in this quadrant, and again up here in that quadrant. So there would be the sketch of my function. Okay, the types of questions we're going to see in the assignment is determining which values of x make the function 0, which values of x make the function undefined, and which make them indeterminate. So in this question, the rational has been factored for you already. Here's what I would suggest. First of all, list the values that make the numerator 0. So the value that makes the first factor 0 is 2, and the second factor is -5. For my denominator, I would list the value that makes the first factor 0, 2, and -6. Now, let's answer the 3 questions they're asking us. They want us to find out what value of x makes the function 0. Well, remember, if it makes the function 0, it's an x-intercept, so it makes the top 0 but not the bottom. So what's the only x value that shows up in the numerator but not the denominator that makes it 0? Well, that value would be -5. For making the function undefined, those are values of x that make the denominator 0 but not the top, so that would be 0 and -6. Finally, values that make the function indeterminate are values that make both the top and the bottom equal to 0, and that would be the value of 2. Okay, so we had a little technical difficulty there, but we seem to be going good now here. So again, the value that makes my function indeterminate is the value that makes both the numerator and the denominator 0, and that would be the value of 2. Okay, let's try this next example. And in the next example, the only difference between this example and the previous one is that this one is not factored. So the first thing I need to do is factor the top. So if I take out an x, I'll be left with x cubed minus 8. And the bottom is a difference of squares, so x minus 2, x plus 2. And again, we can factor x cubed minus 8, because that's a difference of cubes. So this is going to be my first factor of x. Remember to factor a difference of cubes. I take the cube root of the first term, same sign, cube root of the second, square the first term, multiply them together, and square the last term, and the bottom doesn't change. It's still x minus 2, x plus 2. Now we're going to list the values that make the numerator 0. So it's going to be 0, 2, and remember, this guy here is prime, so nothing will make that 0. And for my denominator, I have 2 and -2. So now let's answer the question. So what makes the function 0? Well, the only value that makes the top 0 and not the bottom is going to be the x value of 0. What makes the function undefined? Well, the only value that shows up in the denominator but not the top is going to be -2. And for part C, the value that makes the function indeterminate, well, that's the x value that makes both the top and the bottom 0, and that would be 2. So those 2 examples are going to be very similar to the types you're going to see in your assignment. Okay, the last question here, they're giving us some different functions, and they want us to determine whether the function is a whole, a vertical asymptote, or neither at x equals 1. So if it's neither, that means it's going to be defined at x equals 1. So in part A, we're given a linear function, and there is no denominator to start with, so there are no points of discontinuity. So f of 1 actually equals 1 minus 1, which is going to be 0, and that is a defined point on my graph when x is 1, y is 0. So that answer would be neither. Okay, for B, we are given that f of x is equal to x squared over x minus 1. And if I plug 1 into the function first, I'm going to end up getting 1 squared is 1 over 0. And that indicates to me that 1 makes it undefined. So therefore, x equals 1 is going to be a vertical asymptote. Another way to think of it, this factor x minus 1 has a non-permissible value of 1, and it doesn't cancel out with any factor in the numerator. So therefore, it has to be a vertical asymptote. Question C, we're given that f of x is equal to x times x minus 1 squared over x minus 1. And notice if I was to plug 1 in, I would get 0 for this factor and 0 for this factor. So I would get 0 over 0, which makes it indeterminate. So now I would have to look at simplifying. Well, this factor in the bottom cancels out with that factor in the top, and I'm left with x times x minus 1. So I no longer have a denominator, so I cannot have a vertical asymptote. So therefore, x equals 1 in this case would be a hole or a POD. And to figure out the y-coordinate of the hole, I'd plug 1 into here. Now to get 1 times 0, which is 0, so the point of discontinuity would actually be at 1 and 0. Okay, for the last one, we're given that the function f of x is equal to x times x minus 1 over x minus 1 cubed. Again, putting a 1 in gives me 0 over 0, which should be indeterminate. Now I have to simplify, so this cancels out with one of those. So I'm left with f of x equaling x over x minus 1 squared. Now, my value of 1 will make the top 1, but the bottom 0, so 1 makes it undefined. And this factor of x minus 1 hasn't been completely reduced in the denominator. So therefore, x equals 1 is going to be a vertical asymptote. All right, you're going to have a chance to practice this in the assignment as well. I believe number 17 is a question like that. So there is your assignment for today from page 24. So give those a whirl and see how you do.